When we design autonomous operations at an enterprise scale, we are ultimately building complex mechanical systems structured around non-deterministic, highly unpredictable AI engines. In an agentic workflow, a large language model does not just run once, it loops. A microscopic hallucination or logic error in a single prompt compounds with every cycle, quickly generating catastrophic downstream outputs. Traditional AI assistants were built for single-turn conversations. They lack the rigid software engineering guardrails required to survive unattended in production environments. Writing a Python script to call an API is an experiment. Deploying thousands of autonomous agents to execute business operations requires the same mechanical constraints we apply to critical infrastructure software. Over the last 5 consecutive beta releases, the OpenClaw team shifted their entire focus. They stopped building a tool and started hardening a platform. Instead of adding cosmetic AI capabilities, OpenClaw 10 prioritizes software engineering constraints, strict data typing, deterministic testing protocols, and isolated execution environments. This linear flowchart shows a baseline AI workflow operating on 3 nodes: input, model processing, and output. At enterprise scale, this architecture fails. If the model returns an unexpected string format, the error cascades immediately, breaking the output loop. To stabilize this system, we need to systematically layer the engineering upgrades introduced in OpenClaw 10 over this baseline. Forcing non-deterministic AI models into strictly typed, rigorously tested engineering environments is a mandatory step for enterprise reliability. We start at the foundational logic layer of the agent codebase. Loose typing and unhandled edge cases are fatal in autonomous logic. An agent that cannot verify the exact data structure it received will eventually corrupt its own context window. This stack diagram maps the upgrade. The agent logic layer is enveloped by a firewall of TypeScript compiler checks. Inside, rules like implicit return detection analyze logic. Packets with dangerous side effects are blocked and flagged before execution. Simultaneously, override validation enforces strict class hierarchies, preventing inheritance errors when deploying dozens of specialized agents in a shared environment. But static compiler checks only secure the code before it runs. We also need to secure the dynamic runtime. Legacy testing frameworks struggle with AI environments because they expect outputs to match a single, rigid string. When an LLM phrasing varies, the test fails, creating false negatives that stall development. OpenClaw solves this by integrating stricter Vitest linting rules directly into the ecosystem. By better handling disabled and conditional tests, developers can create dynamic test suites that accommodate the varying availability of external APIs. Safer matcher and expectation validations seams the system to verify the structural state of the agent's output, rather than relying on brittle exact text matches. With improved hook safety ensuring teardown processes run perfectly, continuous integration builds stop failing from silent memory leaks. The real-world impact is measurable: fewer hidden bugs, cleaner upgrades, and predictable builds. Combining strict TypeScript rules with Vitest validation reduces the logic to a series of verifiable states, ensuring the agent follows its programmed path. Securing the logic is the first step. Now we zoom out to the broader workspace and deployment environment. Scaling complex AI models demands fast, consistent continuous integration pipelines. Slow install times and dependency conflicts directly cost engineering hours. This monorepo node map illustrates OpenClaw's upgrade to pnpm 11. A central package manager actively routes dependencies to isolated subpackages. The upgrade delivers drastically faster installs. Parallel installations complete without cross-contamination, reducing workspace package conflicts. This package management directly shrinks image sizes and accelerates build times for Docker container workflows and release pipelines. Once the build is fast, the challenge shifts to safely distributing those updates across disparate deployment environments. Pulling an older dependency version into a staging environment can corrupt a database schema, halting production for days. To eliminate this risk, OpenClaw 10 introduces a new beta channel and release management system. System administrators can now explicitly target distinct, isolated release channels to ensure specific environments only receive approved builds. They can also execute a dry run mode, which calculates the entire update logic and outputs the proposed dependency tree without writing files to disk. These dry runs and explicit channel targeting mechanisms prevent accidental pre-release downgrades. Robust workspace management and fail-safe update pipelines ensure that scaling infrastructure does not destabilize currently deployed production models. Finally, we pan out to the macroscopic architecture to examine how the system routes model queries. Purely cloud-dependent API orchestration results in higher latency, repetitive inference costs, and requires transmitting sensitive data outside the firewall. This architecture shows OpenClaw 10's provider-level local service startup support. A local circuit sits alongside the cloud API pathway. Before an execution request, the orchestrator sends a preliminary probe to verify the hardware node. It then automatically launches the local AI model service on demand. This capability streamlines integration with any OpenAI-compatible inference system across completely isolated environments. The result is a hybrid infrastructure. You balance heavy analytical reasoning on cloud models with fast processing on local LLMs and edge network hardware. This architecture improves two metrics. It maintains data privacy for sensitive workflows and reduces the cost of repetitive inference tasks. This dynamic routing redirects data traffic, keeping sensitive information inside the internal network perimeter. Local inference orchestration severs an enterprise's absolute dependency on external cloud providers, granting sovereignty over sensitive automation workloads. Across 5 consecutive beta releases, we see a complete architectural transition. This composite diagram shows the integration. TypeScript and Vitest enforce the logic layer. pnpm 11 accelerates the pipeline, and local service manages the hybrid hardware. Rigid engineering safeguards provide more value to integrators than cosmetic AI features. This engineering focus correlates with OpenClaw's growth on GitHub and its rising enterprise adoption. OpenClaw 10 serves as the foundational operating system required for autonomous business.